Okay, we're going to pick up with our lecture in this podcast, continuing on with talking about the history of life on Earth, and we got a few other topics to deal with under that area. Um, and one of those is we've talked about fossils before, but we haven't talked about how um, we kind of interpret those and make different inferences from those. And there's a close relationship between geology and biology when it comes to looking at living things in the past. And that is because the evidence we have about those living things in the past are leaving fossils, which are part of the geologic record. And so geologists have put together kind of a framework for these fossils and things that they've found in the past. And so fossils are found, interpretations are made about those fossils, and then based on where they're found, and we did talk about this, where they're found in the layers of the earth, they're either older or considered to be have died longer ago or more recent if they're found higher in the strata. And so geologists from that evidence have put together a time frame or time scale. And that's what this is right here. And it kind of puts all of that fossil record in this timeline where we have fossils that died or in the layers of the earth further down would be placed here, and animals that are in the strata more recently would be placed up here. Now, this time frame is called the geologic time scale, and geologists have divided it up into eras and well, epochs, and then eras, and then periods. Um, but what I want you to recognize from this are the four major eras. All right, so we have the Cenozoic era that takes us up to the present. We have the Mesozoic, that's kind of this middle time frame, and the Paleozoic, which is down here. And before that time, we have the Precambrian. Cambrian, I do want you to be familiar with. It is a period within the Paleozoic, and the Cambrian is a very important time frame because most of the animal phyla that we have today, those body plans are recognized in this one time frame, and that's called the Cambrian period. And that Cambrian, and so because of that, biologists sometimes refer to it as the Cambrian explosion. And if you can see that right here, that's what that says, Cambrian explosion. And so that's a very interesting phenomenon, is finding that many body plans abruptly in the geologic record. It's really not what Darwin predicted. Darwin predicted a slow, gradual appearance. And so because of that, some biologists, they have different ways of viewing this historical evolution or the history of life on Earth as either a gradual appearance of things or a quick appearance of things. And that is called punctuated equilibrium. So a very famous um, more modern evolutionist is the one that coined that term, Gould, Stephen Jay Gould. Um, but punctuated equilibrium is that organisms appear abruptly, like the Cambrian explosion, and then stay constant for long periods. Darwin was more of a gradualist. That's the opposite view, and some evolutionists are gradualists. So there's not a consensus on exactly how quickly this may or may not have occurred. So anyway, this is the geologic time scale, and they put dates on it. Now, dates, when you find a fossil, of course, there's not a date. So how do we get dates for these things? We have two methods for dating things in the past. We have what's called a radiometric dating method, and we have a relative dating method. Now, relative is just saying that this is found further down in the strata, so it is older, it died longer ago. All right, so that doesn't really give us a number. The way we get a number is called radiometric dating. And radiometric dating is using the decay rate of compounds or elements that are in the object that you're dating. So chemists know that these compounds will decay at certain rates recognized in the lab today. So if we find an object with this atom in it, or these atoms in it, they decay and also when they decay, they turn into a different type of element. So for instance, we've mentioned some examples here. Uranium lead is one in our outline. Uranium breaks down, it's radioactive, it breaks down, and it turns into lead at a decay rate that we can recognize in the lab. So if we find an object that has some uranium and a lead in it, a rock with a fossil imprint or something, we can measure how much uranium and how much lead is in that object. We can take that decay rate that we know is occurring in the lab today, we can apply that to those two numbers, and that'll give us a time of when that rock originated. All right, so it's a method of getting a date for something. Now there is some assumptions we have to make for that dating method to be correct. I'd say most geologists would agree with those assumptions, and but there are some that have problems with making those assumptions about these things. We do list those assumptions in your outline, um, but the assumptions are that the sample contained no daughter product. So in the uranium lead, we have to assume that rock only had uranium when it formed. If it had any lead, we don't know if we're measuring the lead that it had when it formed or the lead that came from the uranium. So we have to assume that. And we weren't there when it was formed, so we don't know for sure. The other thing is we have to assume that no uranium or lead came in or out of that object in its whole existence. So that's the other thing. If that happened, then our numbers are not giving us an accurate time. The third is that that rate has to have been constant. We can look at it in the lab today and see what that rate is, but we have to assume it's been constant the entire existence of that rock. All right, so those are assumptions for that dating method to be correct. But that's all we have. That's our method for getting a date for something. All right, so the another topic of interest for the history of life is looking at the continents and how the geology, still dealing with geology, how the continents on the earth got to the point they are today. So there's a predominant theory about that in geology, and that is that all the continents at one time were together in one giant landmass. Alfred Wegener developed this theory and gave a name to that landmass. He called it Pangaea right here. All right, so he gave a name to that theoretical landmass. So the idea was that all the land was right there, and then it started slowly diverging. The first diversion was to split Pangaea into two continents. He gave theoretical names to those continents. He called those Laurasia and Gondwana. So those are in your outline. I do want you to be familiar with those. And then those slowly diverge till we get to the place that we are today. So that's a very common theory in geology. One thing that's used to support that is it's called continental drift is the name of it, is that there are plates, crustal plates where there are fault lines that run through those, and that those fault lines where we have a lot of seismic activities, volcanoes and earthquakes, things like that. So we do have these fault lines, and we know these plates come in contact. So the theory is they're plate tectonics is what that's called. That is what moved the things around. All right. Okay, a couple other topics to talk about, and then we'll wrap it up. And this is the last lecture for this unit. Um, so one is in looking at the history of life on Earth, we recognize a few things when studying those fossils and where they're found. that there's a few instances where there's a lot of fossils found in one layer in the earth, and of some similar animals. And those that when that occurs, there's a lot of death that occurs rapidly. We call that a mass extinction. So developing theories about what caused that mass extinction is important. And one of the major mass extinction is the dinosaurs. So we have that Cretaceous extinction where most of our dinosaurs went extinct, and so there's different theories about that. I don't know about this one, but there's some different theories about what caused that. And your book shows this one, and this is probably the most predominant theory about what caused that mass extinction, the Cretaceous. There's been some other ones, but that's the big one. And that theory is that it was caused by a crater hitting the Earth, an asteroid hitting the Earth and causing kind of a dust cloud to cover the Earth and really limiting the sunlight and life, and the larger animals would all die out, like the dinosaurs. That's a very predominant theory. They even have a crater in the Yucatan Peninsula where they think maybe this crater is the exact spot that this crater hit that caused this dust cloud to occur. That's a predominant theory. There's other theories out there. Saw on the Discovery Channel not too long ago a theory about an ice age, a long ice age, causing the death of larger animals trying to migrate, to move, and just dying during that migration. So that's a theory that's been put out there. Some type of disaster caused this mass extinction, whether it's floods. There's different flood theories, um, um, asteroids, ice ages. Uh, different types of earthquake or geologic activity that cause these. So, but we have a few of them. Cretaceous is our big one, and so explaining those are important. And a couple other things. We talk about concepts in this, looking at macroevolution like convergent evolution. That causes a problem for trying to explain things that are similar in animals that don't have a relationship with each other. And convergent evolution just says this occurred in different organisms. For instance, like the wing, we see wings in insects, birds, and bats. Bats are mammals, and so those are three independent types of organisms, not really closely related in any kind of scheme of evolution. Um, so one explanation of that is they converged, that this was a trait that was beneficial, so they converged with this trait. Another concept that we mentioned is mimicry. This is when an organism takes on or adapts a trait similar to another organism for survival. So they call that mimicry. So all these are just different ideas and concepts related to study of the historical evolution where we don't have direct observation and we have to make inferences and theories based on the evidence that we have at hand. All right, well that ends our lecture for this topic and for this unit. And so that will end it.